In this lesson, we're going to be talking about the normal approximation to the binomial distribution. So in this lesson, we're trying to use the normal curve to approximate a binomial probability. So if you remember a few chapters ago, we talked about the binomial setting where we have probabilities that can be classified as either successes or failures. Events needed to be independent of one another, and the probability of success needed to stay consistent from one trial to the next. And we have a fixed number of trials. So that was our binomial setting. And we had a binomial formula that we could use to calculate those probabilities. We could also use the binomial calculator functions, binom PDF, and binom CDF. So now what we're trying to do is we're trying to use the normal curve to approximate those probabilities instead. Now, if we want to use the normal curve, we have to do a check for normality. That check says that when we multiply n times p and n times q, we have to get a number that's at least 5, so 5 or greater, where n is going to be the number of the number of trials. P is going to be the probability of success, and Q is going to be the probability of failure. If we multiply n times p or n times q and we get a number less than 5, that means that the normal curve is not going to be accurate in estimating those probabilities, and therefore we shouldn't use it. So we should go back and just use the binomial formula or one of the calculator functions for the binomial distribution. All right, let's take a look at our first example. This example says a magazine reported that 6% of American drivers read the newspaper while driving. If 300 drivers are randomly selected, find the probability that exactly 25 say that they read the newspaper while driving. I'm just going to identify the variables first in this scenario. So this 6% would be the probability of success, or P. We're selecting 300 drivers, so that's N. And we want to find the probability that exactly 25 of them read the newspaper while driving. That would be X. So let's first see if a normal curve can be used to approximate this probability. We're going to multiply N times P and N times Q and ensure that those are at least 5. All right, if we multiply 6% times 300, we're going to check to see if that's at least 5. I'm just going to go over here to this calculator. 300 times 0.06. That gives me 18. So 18 is at least 5, so that passed the check. Then I also need to multiply N times Q. So if the probability of success is 6%, that means the probability of failure would be 94%. And if 6% of 300 is more than 5, it is guaranteed that 94% of 300 is going to be bigger than 5. But just to show that, get 282, which is definitely at least 5. So since it passes both of these checks, we can use the normal curve. Okay, so here's my normal distribution. Notice I do not have a mean or a standard deviation listed in this prompt. So I'm going to have to go back to the binomial setting and think about how did we find the mean and how do we find the standard deviation for binomials. There were a couple formulas that we talked about back in the binomial unit. We said we multiply n times p in order to get the mean. Notice we've already done that with the first check. So our mean is going to be 18, n times p. 6% of 300 is 18. To find the standard deviation, we multiply n times p times q and square root that value. So for this, I'm going to multiply the 300, which is n, times the probability of success of 0.06, and times the probability of failure of 0.94. I'm then going to take the square root of that number, and that's going to give me the standard deviation. So our standard deviation is approximately 4.11. Okay, I'm going to label the mean in the center. And of course, I just listed the standard deviation off to the side, so I'd have it there. Okay, so now I am going to find the probability that exactly 25 read the newspaper while driving. So 25 would be on the right side, but notice that it doesn't want less than 25 or more than 25. It wants exactly 25. So there's no area for me to shade. If you remember from geometry, lines have no thickness. But since the binomial is a discrete distribution and the normal curve is continuous, I need to also include the numbers that would be rounded to 25. So that would be 24.5 up to but not including 25.5. So we use what's called the boundaries. So we subtract 0.5 and add 0.5, and that gives us a width. And those would be all of the decimal values that would round to a whole number of 25. So I'm going to find the area between them. We've talked about calculator functions for the normal curve, so I'm just going to show that. I'm going to use normal CDF. The shading starts at 24.5. The shading ends at 25.5. The mean we found to be 18, and the standard deviation is 4.11. I'm going to go to the calculator and find that probability. So that calculator function is second vars and option 2. I'm going to enter those numbers like I just said a second ago. And we get a probability of 0.0229. Again, I rounded that to 4 decimal places. That is pretty typical for probability answers. Okay, the next example says, of the members of a bowling league, 10% are widowed. If 200 bowling league members are selected at random, find the probability that more than 20 will be widowed. Again, picking out important information here. We have the probability of success, which is the probability of being widowed, is 10%. We're selecting 200 bowling league members, and we want to find the probability that more than 20 of them are widowed. Let's do our checks for normality first. So n times p and n times q have to both be at least 5. If I multiply n times p, that would be 200 times 0.1. That gives me 20, which is greater than 5. And then 200 times 0.9 is that at least 5. And that gives me 180. And those are both at least 5. So it's therefore normal. Here's my normal curve. We just multiplied n times p to find the mean, which was 20. So on average, there's going to be 20 widowed players in a bowling league. Notice that we want the probability where x is greater than 20. However, Before I shade that, again, we are on a normal curve, which is continuous, and the binomial is a discrete distribution. So we're going to find the boundaries, the numbers that would round to 20. So 19.5 would, and up to but not including 20.5. Now for this particular example, we want the probability that x is greater than 20. So we actually do not want to include 20 in my shading. I just want the values that are greater than. So I'm going to shade from this 20.5 and up. So that's the boundary that I'm going to use. And we do not need these numbers. Well, I need the mean of 20, but this is my x value that we are now going to find the probability of. Again, I'm going to use normal CDF. The shading starts at 20.5. It ends at infinity. The mean is 20, and I did not calculate the standard deviation, but I will right now. The square root of n times p times q. I'm actually just going to enter it like that in the calculator. So, second vars down to normal CDF. My shading started at 20.5. It ends at infinity, 1 second comma for the E, 99. The mean was 20. And the standard deviation, I'm just going to type that in and let the calculator do the work for me here. 200 times 0.1 times 0.9. Okay, I get the answer, the probability of 0.4531. So notice, guys, we are using what we call boundaries in order to find these probabilities. So anytime you have a binomial setting, you have to check for normality and you have to use a boundary. That is either going to be 0.5 subtracted from the value, the x value, or 0.5 added to the value. You will never use the whole number when you're using a binomial situation. That is called a correction for continuity, by the way. Okay, this example says if a baseball player's batting average is 0.32 or 32%, find the probability that the player will get at most 26 hits in 100 times at bat. Identifying our variables, we have P is 0.32. N is 100. And then at most 26, we want x less than or equal to 26. Let's first check for normality. If we multiply n times p, 100 times 0.32, and check to see if that's at least 5, and n times Q, which is 68%. All right, we get 32 and 68. Those are both at least 5. So therefore, it is normally distributed. Here's the normal curve. Our mean, we just multiplied n times p and found that that was 32, so it's centered at 32. We want x is less than or equal to 26. So 26 is falling below the mean. If I find the boundaries for that number, again, I'm going to subtract 0.5 for the lower boundary, and I'm going to add 0.5 to the value to get the upper boundary. Remember, we read this up to but not including 26.5. Now, we want less than or equal to 26. So if I pick the 25.5 as my boundary, I'm not including 26, but I do want to include 26 this time. So I'm going to pick the upper boundary so that I include the 26 in my shading. I'm going to get rid of this number and get rid of that number so we don't get confused. All right, normal CDF. The shading starts at -infinity. The shading ends at 26.5 with a mean of 32 and a standard deviation of the square root of n times p times q. All right, I'm going to plug that in. Selecting that normal CDF function. The shading starts at -infinity, so -1 E99. The shading ends at 26.5. We have a mean of 32 and a standard deviation of 100 times 0.32 times 0.68. Okay, we get a probability of 0.1192. And again, remember guys, this is a probability, so we could change this to a percentage if we wanted, or leave it as a decimal. Fraction format would also be acceptable, but of course, that would be a lot of work. So let's just leave it as the decimal. Okay, this last example is a U-try. So read through that, see if you can find the probability. Don't forget to check for normality and also think about boundaries because we always use boundaries for binomials. Pause the video here, see if you can find that probability, and then unpause the video to see the results. Okay, here are the results of that last example. N times P and N times Q were both at least 5. Therefore, we could use the normal distribution. Since we wanted exactly 85, we had to use both boundaries. So 84.5 and 85.5 were the boundaries that we used, and we wanted between them. So normal CDF of 84.5 to 85.5 with a mean of 80 and a standard deviation of the square root of 100 times 0.8 times 0.2. You can see the calculator function there, and actually I'll show this screen as well, just in case it's a little bit easier to see what was typed in. And when we do that, we get 0.0457. as the probability, or 4.57% if I wanted to write it as a percentage. Okay, now, ladies and gentlemen, all of our examples that we looked at, the N times P and N times Q were at least 5. That means that we can use the normal curve to approximate that probability. But keep an eye out. If N times P and N times Q are not at least 5, you cannot use the normal curve to approximate the probability. So that means that you would have to go back and either use binomial formula or one of the calculator functions for binomial instead. So for instance, if this particular example, let's say the probability was 96%. So there's a 96% chance that an employer is going to check the educational background of an applicant. So now when I multiply N times P, 100 times 0.96, that one is at least 5. That's 96 is at least 5. But when I multiply N times Q, I only get 4. That is not at least 5. So I would not be able to use a normal curve because this is a non-normal distribution. So the probability of success is so high, the probability of failure is so low that it's going to be a skewed distribution. So we can't use the normal distribution to approximate it. So what you would have to do is to find that probability of exactly 85, you could use the binomial formula, which remember looked like NCX times P to the X, Q to the N minus X. Okay, so this would say 100C85, 0.96 to the 85th, and 0.04 to the 15th. I could do that. Or I could use a calculator function. Since we want exactly, it would be a binomial PDF scenario. So I would hit second vars, binomial PDF. That's choice A in my calculator. Oops. Oh, let me exit out of there first. Sorry, guys. Let me try that again. Second vars, binomial PDF. And we have to tell the calculator N, P, and X. So N is 100. The probability, remember I changed it to 0.96. And then the X value, I want exactly 85. And that's how I would find that probability, since I could not use the normal curve to approximate it, since it violated the N times P and N times Q check. Okay, so just to recap those binomial PDF is used when you want exactly one X value, and binomial CDF was when we wanted multiple X values starting at 0 and going up to a specific number. Okay, so if it fails those checks, guys, it doesn't mean that you can't find the probability. You just can't use the normal curve to approximate that probability. So you're back to the binomial situation. Okay, this concludes the lesson for today.